Hello everyone, today we're going to learn how a turbofan works. So on the screen, you can see a turbofan. One main thing that you have to understand is that there are two ways that an air can flow. So two ways. The first is the core. The core, I'll draw it as a red, and so when the air is going in the turbofan, it's going to go through the core, which means it's going to go through this. This is the core. All right. The second way that an air can pass through the turbofan is the bypass. The bypass is what it sounds like. So I'll label that as blue. So when air is coming in, it does not go through the core, but it goes through the bypass. One key note that I want to mention right now is that majority of the thrust that is generated from a turbofan comes from the bypass. So if you think about it, a turbofan is simply a large fan. Then why do we need core? Why don't we just operate it with a fan? Well, we're going to talk about it. But before we get into the specifics of that, I want to label each part of the turbofan. So that way you get familiar with each part. So let's begin. From the ambient airflow, which I will denote this as probably 0, here to the entrance of the turbofan, we call this the inlet or the diffuser. What do you think happens to the air in an inlet or diffuser? Do you think air accelerates or air decelerates? The air actually decelerates, that's right. So air decelerates in an inlet. I don't have enough space to write everything down, so I'm just going to talk about it. And here we have the fan. And we all know what a fan does. A fan accelerates the flow. It's responsible for sending air to the rearwards of the turbofan. So what do you think happens to the pressure? Do we all know Bernoulli's equation or Bernoulli's principle? What happens when velocity increases? What happens to the pressure? It decreases. So pressure increases, pressure decreases with increase in velocity. In a more accurate term, you actually call this static pressure, but we can talk about this in another time. This part right here is the compressor. Compressor is important because it actually increases the efficiency of the thermal efficiency. So in a compressor, air, do you think it's accelerated or decelerated? Well, actually, when we're analyzing turbofan, we assume that the velocity is negligible in the compressor, the combustor, the turbine, except for inlet and nozzle. So we will organize this at the end of the video. But for now, what we need to know is that the total pressure is increased and the total temperature is increased. If you know how to draw a TS diagram, I recommend you to try to draw a TS diagram right now. So what happens on the next one? What's this part called? This part is called the combustor. This is where additional chemical energy is added to the air. The air is expanded, added with the fuel. Fuel is combusting, and the air now have a lot of energy. What is this part called? This part is called the turbine. Turbine is where the energy of the airflow is extracted and is used to power something. And we're going to talk about that. Think about it. What do you think turbine powers. Turbine's extracting the energy from the airflow and it's powering something. What other parts in the turbine is moving that needs to be powered? The last part that we have here is simply a nozzle. And like I said, in a nozzle, we assume what? Velocity is not negligible. In a nozzle, the velocity is not negligible, so what happens to velocity? Velocity is actually accelerated. It increased. So pressure is actually decreased. So it's kind of opposite of an inlet, right? Inlet, velocity is decreased, it's decelerated, and pressure is increased. However, in a nozzle, velocity is increased and pressure is decreased. Interesting, huh? And I'll give you the answer for what the turbine powers. I'll probably use green. So turbine extracts energy from the flow. A more correct term would be power, extracts power from flow, from air flow. And what do you think turbine powers? Well, it powers the fan. You are right. But what other things is it powering? It's powering the compressor. So without the turbine, the compressor will not work and the fan will not work. Now, I drew a very quick turbofan right now because we want to go through the parts of the fan. We went through the parts for the core, but we didn't really go through what goes through in the bypass. So obviously we have the same, the inlet, right? We have the inlet here. And obviously it goes through the fan, but it doesn't go through the core. It goes through here. And there's really nothing. It's just kind of a nozzle. We call this the fan nozzle. So in the entire process for a bypass, so this is what the bypass experiences. So I'll say bypass experience. I hope his experience is good. Bypass experience. So it experiences no heat. So it's adiabatic. And we're going to talk about it in the next part about our assumptions, but it's isentropic. I want to note some interesting things. So we usually say T naught is the ambient temperature, which is our sea level temperature, our normal temperature at sea level. And this is usually 288.15 kelvins. This is just the absolute temperature. Try typing in 288.15 Kelvin to Celsius or Fahrenheit, and you'll realize it's a very comfortable temperature. Well, the temperature at the exit of the flow, TE, or we denote it as T19 in propulsion, if you want to be fancy, this is also 288.15 Kelvin. So there was no change in temperature whatsoever in the exit flow. What do you think about pressure? The normal pressure that we experience, is 101 kilopascals. Or if you're more familiar with, the English units, this is 14.7 psi absolute. Well, the pressure actually does not change at all. So pressure 19, it's also the same, stays the constant. This is also, sorry, I clicked the erase button, is 14.7 psia. Interesting, huh? So the only difference is the incoming airflow. So if we say, I don't know, this is like, 200 meters per second, then it's going to be higher. Like exit is going to be higher than the inlet velocity. So along the way, I've told you some assumptions that we use to analyze a turbofan. And you might be a little confused now because I went over it very quickly, but I'll go over it right now. So the first one is velocity of the airflow is neglected. Or you can say it's negligible. For compressor, combustor, turbine. But it's not negligible for inlet, or it's also called a diffuser, and the nozzle. The second assumption that we use is we assume that all parts, so inlet, inlet diffuser, nozzle, compressor, turbine, they are all operate isentropically. So they're all isentropic process. And an isentropic process, it's not a complicated concept, but it's a very fundamental concept. And I don't want to spend this video on it, but I'll give you succinct information on it. So isentropic process means that the process is both adiabatic, which means there is no heat addition or heat rejection. So it's kind of like protected in a very thick styrofoam, and it's not a very good heat conductor. Actually, it's zero heat conductor, right? So, and it's reversible. So reversible kind of means like there's no friction. If there's friction, there's losses, and the world is not perfect. Like the world is not perfect. But reversible means there is no friction, the world is ideal, it's perfect. Like if you see a car, you say it's a cylinder. If you see a building, you see it's a rectangle. All that good stuff. Except, so it's all isentropic process except combustor, because we are adding heat. And it's not, that means this is not adiabatic. So this is probably the two big assumptions that we had to go through in order for you to fully understand what we talked about. I want to talk about force. The reason is because when we talk about a turbofan, we are mostly focused on how much thrust it generates. In fact, thrust and force have the same unit. If you take in high school physics, you would know that force is mass times acceleration. The unit of this is just kilograms times meters over second squared. However, we can rewrite this as mass flow rate times velocity. And this has the same unit, kilograms over second times meters over second. So this is also kilograms meter over second squared. So they have the same unit, and usually we prefer this term. The reason is because whenever we're dealing with an engine, especially a turbofan or a turbojet, if we have a turbofan here, then air is not stagnant. Furthermore, air also has mass and is flowing through the engine. Therefore, we don't talk about it just mass of air or air mass. We just call it the mass flow of air. That's why we prefer the mass flow rate times the velocity. I do want to write the complete thrust equation for a turbofan, so let's go ahead. So the complete thrust equation is the total thrust is probably the thrust from the core plus thrust from the bypass. And like I said, thrust is a force. And what is a force? Force is just mass flow rate times velocity. But what is fundamentally a force? it means there's a change in momentum. There's a change in momentum because remember, we can rewrite force like this, and mass times velocity, that's just momentum. Anyways, it's really good to know where the force comes from, what is force, and knowing different forms of force. So we have thrust. So this one, I would say mass flow rate that goes through the core, I'm just going to denote it as m dot c, times exit velocity. So exiting at the nozzle, right? It's not a fan nozzle, it's the core nozzle, minus the incoming airspeed. Well, how about the bypass? Well, it's the mass of the bypass and the velocity that exits the fan nozzle. It's not just a nozzle, it's a fan nozzle minus incoming airflow. And if you add them up, then you have the total thrust equation for a turbofan. And what I want to say is the thrust from the core is much less than thrust from the bypass. One of the reasons being is because there is a higher efficiency, overall efficiency for a fan compared to what the core. And we can probably learn that in the future videos. I guess lastly, we can draw a simple TS diagram where everything is ideal, obviously. So we're going to draw a TS diagram for the core and TS diagram for the bypass, okay? So the left one is going to be for the core, the right one is going to be for the bypass. For the core, we have this usual Brayton cycle. If you don't know what a Brayton cycle is, I recommend you to search it and learn it. Brayton cycle. It's B-R-A-Y-T-O-N. And I will probably give these numbers because it's important. And I will erase. Okay, so what do you think happens at 1? It's isentropic because the entropy, there is no change in entropy. It's going straight up, but there is a change in total temperature. Well, it's called isentropic compression. So this is for the inlet and the compressor. Inlet, comma, compressor. How about 2? We have increasing entropy, but we also have increase in thrust. I mean, not increasing thrust, we have increase in temperature. That has to be combustion. That might have been hard because we said the process of the combustion is not isentropic. So we're going to say this is isobaric, which means constant pressure. Isobaric heat addition. And this is combustor. So for 3, we have isentropic, because as we can see, there is no change in entropy. Isentropic expansion. And this is the turbine. Turbine is isentropic, but it's taking away energy from the airflow, so it's reducing the total temperature of the airflow. What about 4? I'm going to write it on the top. This is also isobaric heat rejection. This one is not part of the engine itself, but what happens is in nature when you obviously let out a hot air, then it kind of diffuses with the rest of the air and reaches equilibrium temperature. Now, this is basically what a TS diagram looks like for the core of the turbofan. What happens to the bypass? Did we say the flow is adiabatic? Yes. Did we say the flow is reversible? Yes. So is it isentropic? Yes. So is there any silly thing that goes like this or like this? No. There is nothing like that. So what happens is just straight up. So what happens is actually the inlet increases the temperature a little bit. The compressor increases the temperature a little bit. Oh, sorry. This is until the end. This is the not the compressor, but the fan, because the fan works like a compressor. So the fan increases your temperature until here, and then it stays up here, and then this is like the final temperature, kind of funny looking TS diagram, huh? So that was it for the Turbofan introduction. I might cover more of it in the future video, but thank you for watching. If you liked that video and was educational for you, click that subscribe button and click the like button. It really helps me and the channel.